To develop the space between the Earth and Moon and build space habitats and power satellite constellations, orbital data centers, and Mars colonization fleets, we're going to need a lot of mass in orbit. Fortunately, there's already 73.4 quintillion tons of mass in Earth's orbit. We call this giant ball of feedstock material just waiting to be used the Moon. But in order to exploit this Moon material, to export liquid oxygen to low Earth orbit, decimating what remains of the launch cost barrier, and build habitats for humanity and celestial-sized telescopes, and construct terawatts worth of power satellite platforms to destroy Exxon's market share and save the sea turtles, we're going to need a mass driver, or 10, powered by gigawatt-sized fields of solar cells with kilometers of aluminum transmission cables and all the other corresponding grid hardware. And to supply these mass drivers with moon mass, we're going to need vehicles and machines that can carve them out of the lunar surface. And all these things, these vehicles and the infrastructure and energy grid, all of them will need to be made on the moon, out of the moon. Which means we need a lunar industry capable of refining regolith into metals and materials, and workshops capable of turning those metals and materials into machines and useful things. In order to build a lunar industry such as this, we're going to need building materials, bricks and pavers for radiation shields, and roads and platforms, and landing pads and cylinders for pillars and pipes, and bricks and blocks and beams for all kinds of other things. So the big question is, what materials do we use to build things on the moon? This is cast basalt. To cast something simply means we melt it, then form it into whatever fun and useful shapes we want using a mold. We cast metals and glass all the time. Here we're doing it with rocks, specifically basalt rocks. Not all rocks are good for casting, owing to their differing chemistry and compositions. Basalt is mafic. It's fine-grained and relatively rich in magnesium and iron. Its minerals begin melting at relatively low temperatures, around 1200 degrees Celsius, and they all melt roughly at the same time, producing a fluid, homogeneous melt. Granite, on the other hand, also an igneous rock, is felsic, dominated by quartz and alkali feldspar. These minerals have different, much higher melting points. Quartz won't melt until 1700 degrees Celsius, for example, and they melt incongruently. Then, when the melt cools down, these different materials begin to crystallize at different temperatures with different rates, creating stresses you cannot remove unless you subject the stuff to very high pressures over long periods of time. The same high pressures over long periods of time that it took to form the granite in the first place. So, basalt's ability to be melted and cast easily makes it somewhat special among rocks. The resulting products of cast basalt are very resistant to abrasion and chemical corrosion, so today they're used as tiles and pipeliners and for high abrasion particle chutes for things like coal and agriculture and for slurry pumps, which should give you some idea of how dynamic this material is and how it can be cast into complex geometry. Cast basalt's material properties are better than concrete in almost every way except for thermal expansion. It has higher tensile strength, compressive strength, modulus of elasticity, and chemical corrosion and abrasion resistance. So we could build buildings out of it, but we don't because it's more expensive than concrete, as it requires intense amounts of heat, closer to metalworking. And this also means putting rebar in it can be tricky since its melting temperature is above the working temperature of most steels. Whereas concrete really just requires lots of water, which we do have in abundance here on Earth, unlike on the moon. Cast basalt can also be drawn into fibers, like glass, and during the 1950s, basalt fiber composites were a serious competitor for fiberglass, with both the US and USSR investing heavily in its development. In the West, however, established glass producers such as Owens Corning had already invested heavily in fiberglass technologies, which offered slightly higher ultimate yield strength and stiffness. So around 1970, these firms formally abandoned basalt research in favor of focusing their efforts into their glass fiber markets. However, the USSR had no pre-established fiberglass market and a lot more basalt resources in the Urals and Ukraine. So in the 1950s, Gosplan, the Soviet State Planning Committee, began heavily investing in cast basalt, allocating state funds to convert existing glass melting works into basalt casting foundries. And because of that legacy, today almost all commercial cast basalt production facilities are clustered in former Soviet states. In the Czech Republic, for example, Utite's basalt casting plant turns out some 40,000 tons of cast basalt per year. So this stuff is great. Wouldn't it be awesome if we had something like it on the moon? Well, we do. The difference between lunar regolith and basalt is really small. The natural iron in regolith has a different oxidation state due to solar wind hydrogen reduction, and besides a few teeny tiny other things like the form phosphorus takes, that's about all. So lunar regolith is pretty much just basalt. How lucky for us that this giant ball of feedstock material also happens to be mostly made out of one of the best rocks for casting. I mean, it definitely didn't have to be that way, and it just further reinforces my opinion that the moon lets us play the game on easy mode. So then, let me ask you, what do you think we should build with on the moon? If your answer was, we should 3D print regolith using imported binders and vulcanizing agents, or make concrete using sulfur and water, then congrats, you're qualified to work at NASA, or ESA, or any other 3-letter agency funding this kind of work. If your answer was, we should use cast regolith, then go back to the 80s, bucko. We don't want those communist materials. We want advanced multi-material additive manufacturing and imported freedom-loving carbon polymer composites.
I'm escaping to the one place that hasn't been corrupted by capitalism. Space!
In all seriousness, NASA and friends fund tons of things as a way to explore possibilities across many different constraints in order to map different strategies, and I'm definitely not against exploring ideas and viability demonstrations, so this is not a critique of NASA for investigating these things. It's more a critique of investigating these much more than cast basalt. The issue with 3D printing and vulcanizing agents is they require imports, while casting regolith does not. The main argument for 3D printing structures is that it requires less steps in the process and less energy since it can be done at room temperature. This energy argument really only matters if you are working within some specific mission parameter, which NASA usually is, to be fair. Say your small lunar lander only provides you with 1 kilowatt of power or something. Then you might want to make things using these much lower energy cost alternatives, but it's only lower energy cost once on the moon. But if you want to develop the moon, then we need to count all the energy used in the entire supply chain, which makes importing vulcanizing agents immediately the most expensive approach. To melt regolith for casting requires about 600 kilowatt hours per ton, so we can probably make 1 ton of cast regolith bricks for about 1 megawatt hour. The ratio of regolith to plastic binding or vulcanizing agent varies, but it's typically something around 15%, meaning for 1 ton of 3D printed stuff, we need to import about 150 kilograms of vulcanizing agent, or plastics. Saturn V spent about 41.9 terajoules to deliver 43,000 kilograms to the moon's surface, or about 0.27 megawatt hours per kilogram, times 150 kilograms equals about 40.5 megawatt hours per ton, compared to the 600 kilowatt hours per ton of cast regolith. And just measuring things in energy cost is a bit misleading because not all energy is made equal. This energy is the most expensive type of energy, rocket energy, which costs a lot more clams than solar panel energy. So maybe 3D printing has less steps involved in the process than brick making and masonry, but it costs about 40 times as much energy from the imports alone. As for the sulfur and water-based lunarcrete type stuff, if you try to source the water and sulfur on the moon, you have to steam out the sulfur and water from the regolith and capture it. And we do have these things on the moon, but not much. So, for example, we have just about 0.1% sulfur in lunar regolith. And for lunarcrete, we need about 12% sulfur by mass. So to produce 1 ton of lunarcrete, we'll need to process about 120 tons of regolith, assuming a 100% recovery rate just to get the sulfur. And whatever water and sulfur we do get, say from the cast regolith process, will have higher priority elsewhere. To my knowledge, there have only been 2 studies into casting lunar regolith since the 1990s. One by the Pacific Space Center and Cisloon, where they investigated making spacecraft joints out of cast basalt using sand molds, and another by Kevin Ferries and friends of the University of Adelaide, where they looked at welding cast basalt bricks together using a laser. I may have missed some, and if so, please let me know in the comments, but from my perspective, it really seems like cast basalt is being overlooked in favor of methods that require either imports or water or both. And many of these approaches quote energy savings as their biggest benefit, but then conveniently ignore the cost of importing the required binders and sourcing the water. And anyways, we have tons of energy on the moon, so why is this the constraint? Why are we funding so much energy constrained research? Could it be low-hanging fruit job creation? Or maybe it's tied to the fact that every university engineering department sold its soul to the god of 3D printing in 2010 and never looked back. Or maybe they just know something I don't. It's entirely possible. I've overlooked some fundamental reason why cast regolith is not a good solution. Although if that's the case, I wouldn't be the only one, since Kevin Ferries and team, the same ones who did that laser welding stuff, also put together this big beautiful lunar construction materials literature review in 2021 and came to the same conclusions as I did. Cast regolith is the most viable production method in the lunar context, but is under-researched compared to other processes. So maybe they have their reasons for ignoring cast regolith, but it just seems to me to be a bit disconnected from reality, because in reality there is tons and tons of energy in space. 1,360 watts per square meter, about 360 watts more than on the Earth's surface, due to atmospheric attenuation. And this is one reason why the space above Earth and the moon can be so useful to life on Earth. The number one determining factor for quality of life is energy use. If we can tap into this clean, golden abundance right above our heads, we can improve life for everyone and everything on Earth, including the environment, ushering in a golden age of abundance and prosperity and advancement beyond our wildest dreams. I mean, space has so much energy, you have to go as far as Mars before energy constraints even become— Oh, right. Mars gets about 40% as much energy as Earth and has some water. I guess that explains all the focus on excreting Levittown turd homes. But for lunar industry, what we lack in water, we more than make up for with energy. So maybe we should explore cast regolith manufacturing a bit more. We talk about sintered regolith a lot on this channel. So why cast it? What advantages does casting have over sintering regolith? Well, sintered regolith is more like a ceramic. So think of tile or terracotta. Sintering requires about half as much energy to produce as cast regolith, and it's stiffer, but it doesn't have as much compressive and tensile strength. In general though, both are useful in their own ways, which is why in the train video I mentioned building your roadway as a cast regolith base with sintered tiles on top, so we get the best of both worlds. We explored sintered regolith a lot in that video. See, I knew trains would really appeal to my audience for certain reasons, so I figured a discussion about sintered regolith could really benefit if it was done through a more interesting choo-choo lens. But we didn't really explore cast basalt much. So let's start by looking at how basalt is cast on Earth today, and then discuss some ways in which it might be different on the moon. The first step is obviously to melt it. The point at which basalt becomes a liquid is called its liquidus point, which is about 1280 degrees Celsius. But to get a good product, we really need to heat it higher than this, up to about 1350 degrees Celsius, so that we can make sure all the particles are completely fused and we get a homogeneous melt. Once this fusing temperature is reached, the melt is then allowed to cool back down to its 1280 liquidus temperature, so that it has as little shock as possible when it contacts the much cooler molds. But the molds aren't cold. Much cooler is relative, as to avoid shot cracking the molds, which are typically made of steel, we preheat the molds up to about 800 degrees Celsius, near the working temperature of steel. The goal is to get these two things as close in temperature as possible, so we heat the molds as much as we can without damaging them, and then cool them melt as much as possible while still keeping it a pourable mold. And by doing so, we are able to avoid forming crack shocks in both the cast product and the mold as well. Once we pour our cast, the next step is to anneal it. When you cool hot cast molds, the outside shell cools and contracts faster than the hotter core. That mismatch leaves residual tensile and compressive stresses locked in the body, which can cause flaws. Annealing is simply holding the cast at a certain elevated temperature long enough that temperature gradients equalize, then cooling it very slowly. This relieves the internal stresses and brittleness and improves its mechanical and thermal performance. The industrial standard for cast basalt is to put casts in a layer furnace, cooling them slowly from 800 degrees Celsius to 50 degrees Celsius over the course of 24 hours. The hard lunar vacuum should provide us with a benefit for annealing, as there is no convection to carry the heat away, just conduction and radiation. For annealing, slower is better. On Earth, we have to spend energy to keep things at elevated temperatures, fighting against their natural tendency to cool to ambient temperature, so we do things like put the casts in layer furnaces where we have to spend energy to slow their rate of cooling. On the moon, we can slow cooling significantly by just reducing the heat conducted away using an insulator, and regolith is a great insulator, so for this annealing step we can probably just bury our molds in regolith. If not, then at least the energy cost of annealing should be significantly reduced. If you can make bricks and blocks and tiles and pillars and beams, then you can make all kinds of buildings and things. But how do you glue it all together? What about mortar? Well, getting these blocks to stick together might be a bit tricky without lots of water, and that's why Kevin Ferries and friends investigated welding basalt blocks together with a laser. The results were mixed. Basalt bricks can definitely be welded together, but unless you preheat the individual bricks to about 750 degrees Celsius, more than halfway to their melting point, then the weld is total crap, with micro cracks and pores causing it to have just 0.9 newtons a millimeter of strength, whereas if you heat the bricks up beforehand, you can get a solid weld with a strength of about 16.5 newtons a millimeter. Much better, but this preheat step would greatly complicate construction and increase costs. Imagine trying to build a wall, but instead of just quickly pasting mortar between each brick, you instead have to painstakingly sit there and wait for each brick to reach over 700 degrees, then carefully weld them together. Maybe we could try pouring on molten regolith as a glue, but isn't this the same thing you're doing with the laser? So shock cracks and pores would likely form here as well, unless you preheat it. This mortar question is quite tricky, but honestly, I don't think we need mortar. Ashlar masonry is a type of stone construction which does not involve the use of mortar. Instead, the blocks are held together by their own weight and how they are placed, and you can actually make quite complex things with this method. But the key here is that our bricks and blocks need to have standardized uniform shapes, which we probably want to do anyways. Mortar is prevalent throughout history because people were just gathering whatever rocks they could find around them, so mortar can glue all these random shapes together into one solid unit. But in rarer cases where stones could be made uniform, which historically did require more effort, this ashlar masonry approach works just fine, and we have many historical examples of this. Perhaps the most famous are those buildings made by the Incas who did not have mortar. Look how precisely placed these stones are. It's almost as if the stones are melted together. The ancient aliens community has argued this is evidence that these were made by aliens and claim these bricks are laser welded together, but as we know, that's not a good solution because of the preheating requirement. It turns out there's actually a kind of reddish mud found in Incan mines called Lancac Alpa, which contains a lot of pyrite, or fool's gold, which is made of iron and sulfur. Pyrite is a quite stable mineral, but there are a few types of bacteria that live in this mud that can oxidize the sulfur from the pyrite, which results in the generation of sulfuric acid in this Incan mud, which can reach acidity levels of up to 0.5, which is 10 to the 4th power times more acid than is needed to weather silica containing rocks via silica gel. In other words, it can dissolve the rocks. When heat and pressure is applied, this gel can recrystallize back into silica, and it turns out heat and pressure is generated when pyrite is crushed by two giant rocks. Pyrite is actually a fuel, and when finely grained can actually self-heat and even combust. This happens with coal too, except pyrite does it 16 times faster, rising from 30 to 90 degrees Celsius in just 3 hours. And this is a real problem in Peruvian mines even to this day. So this red mud could dissolve the rocks, and then over time the silica gel from this could recrystallize, essentially fusing the rocks together. And there are lots of Incan folk traditions of using this mud to glue rocks together and squeezing plant juice on it to catalyze the reaction. Because of this rock melting stuff, sulfuric acid has a long history of use in the mining industry, especially for copper and uranium, and has even been investigated as a possible way to refine lunar regolith, with one advantage of this approach being that it would require lower temperatures, peaking at about 900 degrees Celsius, but this temperature would not need to be maintained for the entire time. It's just the maximum temperature used in this entire process at one point in the process. So it could save quite a lot of energy if we were, say, in an energy constrained environment with lots of water and sulfur. The problem is the lack of sulfur on the moon. It is present, but not in significant, what you might call industrial levels of quantity. But the sulfur and water involved in this process could probably be infinitely recycled, so this is still somewhat promising for the moon. However, sulfur is more common on certain kinds of asteroids and on Mars, which I guess explains why the aliens used this technique when they built these nice cities for the Inca, which was super nice of them, by the way. Maybe they just believed in intergalactic affordable housing or something woke like that, I don't know. Anyway, there's a lot more that could be said, but this isn't a video on Incan alien building techniques, so I'll just recommend checking out this paper if you're interested, which I'll link in the description. But one thing I did want to note, and this is pure speculation, but we all know that the Spanish and Portuguese conquistadors were told local legends of cities made of gold laying further west, like El Dorado. Well, pyrite is fool's gold. So if this red mud technique is true, then maybe these cities really were made of gold. Fool's gold. Oh wait, wouldn't this red mud stuff actually just be a kind of mortar? So this kind of goes against the whole point I was trying to make about historic examples not using mortar. Well, anyways, nowadays ashlar type masonry is quite common since we can manufacture standardized bricks and pavers at scale. You've probably seen walls like this, so if we're casting basalt into standardized molds, then this is a viable option. But if this isn't enough, if you really need these bricks to stick together, maybe the lunar monsoon season is really strong in your area, then another option is just to make these units interlocking, which we can do with a number of different geometries, and this could be especially useful for roads and landing pads, which will experience a lot of different forces. The first thing you're probably going to use bricks for though is to create a radiation shield around your retrofitted wet workshop. It needs to be about 3 meters thick on all sides, including the top, which is going to mean it'll be quite heavy even in low lunar gravity. This weight means it's not as easy as just piling dirt onto your habitat. You're going to need to distribute that weight. Fortunately though, we have over 2,000 years of masonry knowledge to tap into to solve some problems. Look, arches can be built without mortar. Corbel arches are easier to make than true arches, as you simply just stack successive stone or brick layers with a slight overhang. This is called corbelling, and it's been used since the Neolithic. These giant structures called brocks were built in Scotland 2,000 years ago, and if we can make cast basalt bricks, we can corbel them into brocks on the moon. To make them airtight, we can layer the inside of the building with iron plates welded together, similar to how ship bulkheads are made, thanks to the Mist of Time team for this animation. So we can make bricks and blocks and beams for walls and roads and radiation shields and landing pads and many other things. But in the beginning, you're not going to be able to make very much using that little imported furnace and power source. So it's probably best that you use the first bricks and beams to make a thing that will enable you to make a lot more bricks and blocks, something like a solar furnace. Not shown in the last video on solar furnaces was how this solar furnace design can be constructed using medieval carpentry and engineering. Does this not resemble a trebuchet? Except instead of wood, it's cast regolith. Even the joint is made from cast regolith wheels with beams as axles and centered regolith ceramic surface pads as the walls to reduce friction. But now you might be thinking, well, what about those long beams? Cast regolith is brittle, no? Sure, but its tensile strength is about 36 megapascals, or about 6 times the tensile strength of concrete. And according to my handy dandy wood handbook, hardwood beams have tensile strengths of about 100 megapascals. So cast regolith beams will only be about 30% as good as wood. But the moon's gravity is only 16% of Earth's gravity, so you should be able to get away with it. But if not, then to make stronger beams, we can lay pre-stressed rebars in the mold when we cast the beams. This will cost more since you now have to refine metals, but hey, you're the one demanding a safety margin. Another, perhaps less expensive option might be to use tensed mineral fiber rope to post-reinforce the beam. Anyways, once you build this solar furnace out of cast materials made from your little imported furnace, then you can make a lot more things. You can use it to cast more bricks and blocks and beams for more radiation shields and landing pads and roads. But you can also use it to refine larger amounts of regolith, replacing whatever little refining unit you brought with you as well. So you can produce more oxygen, more metals, and cast more materials, which you can use to make more solar furnaces to produce even more oxygen and even more metals and cast materials. Next stop, mass driver. Thanks for watching, and thank you so much to all the Patreon and channel members who make these videos possible. A super thanks to those who send super chats, and I'll see you guys next time.